Yeah. All right. 3.6 properties of linear relations. Okay, so good news is you guys have done this. This was Math 9. We made straight lines. Do you guys remember this equation? It was y is equal to mx plus b.
Yes.
We're doing more of that in math 10. It's just going to be a little bit more difficult, right? But it is the same concept. So a lot of these things should be reviewed. I know it was a long time ago, but we'll go through it again. So in math 10C, we do a lot with linear relations, so straight lines. And I'll just tell you where you guys are heading. And then when we get into like math 20-1, 20-2, we do a lot with like parabolas. So they're going to be shapes like this, or maybe like an upside down one. And then in math 30-1, 30-2, we do that, but then we also do other ones that look more like this one, where it'd be like a, like a squiggly line, or maybe one that goes up like this and then comes back down again. So it's kind of a building block, right? We start off with straight lines. That's kind of the simplest of them. And then we do parabolas, and then we kind of work up from there, right? So a linear relation comes from the word line, right? So that should be a straight line on your graph. And we should also see that if you have a table of data here, that our x's should go up by the same amount and the y should go up by the same amount. This will turn into like rise over run stuff that I know you guys are doing in Science 10 right now, right? Where the rise would be the same for any part and the run would be the same for any part, right? So that's the reason for that. A nonlinear relation, you would see that the numbers that they go up by are different every time, right? So that would be a nonlinear relation. That could be like an exponential relation, as we'll go on later, but for now, yeah, we won't do that. Okay, examples of linear relations will also look like this famous y is equal to mx plus b, where if we have this thing written out as like an equation, so let's say y is equal to 3x plus 2, you're always going to have, like, on your x value, the biggest exponent would be 1 on the biggest exponent there, or in the biggest value of x there. So an example of one that wouldn't be, right? If I had something like this, y is equal to 3x squared plus 2, that's not going to give me a linear relation. Yeah, that one would actually end up looking, if I graph this thing, would look like this. It'd be like a U shape. That's like that 20-1 or 20-2 level. It will be a line if it just has like just an x by itself, or like a degree of 1 on the top there. And that's to put it into this y is equal to mx plus b form, right? Where it's going to just be a straight line there. It could also be rearranged funny though, like in this one. It could be the same type of thing, but it could be like 3y plus 2x equals 1. This would also be a linear relation. It's harder to see because it's not in our nice form of y is equal to mx plus b. But we could rearrange it, right? We could do some algebra and we could get it to just y is equal to something, right? I'm going to show you how to do that later. But for now, this one would be a linear relation because our x value is to the power of 1. So we just know that right off the bat that it's going to be a line. Okay? All right. Other examples where it couldn't be. It could also be this one though, right? Even though this one was just x to the 1, it can't be in the denominator. That would mess things up. It's got to be able to be written in this form, y is equal to mx plus b. Okay. All right. You guys can look at these examples, but I think let's kind of skip through some of them. You guys can go back and look at them for your sake. But let's do number 1 here. Which table of values represents a linear relation? Justify your answer. So A is the relation between the number of bacteria in a culture n and time t minutes. So if I want to figure out whether this thing is going to be a linear relation or not, really what I'm wondering is, do the x's go up by the same amount every time, and do the y's go up by the same amount every time, right? Is it going up by like a straight amount? So what do my t's, which would kind of be like my x's, right? That'd be like an x and that'd be like a y. They're going up by 20 every time, right? 20, 20, 20, right? So I've got that pattern. What about this one? Goes up by 1, goes up by 2, goes up by 4. Okay, I think we can stop, right? Is this thing linear?
No.
No, not a linear relation. right? This thing is actually exponential is what's happening here. So yeah, there's not going to be a linear relation because they're going up by different amounts. And yeah, that's pretty much it for that one. What about this one? So we've got this is like our x, and this is like our y in this case. Well, it goes from 60 to 120, and then to 180. So what's it going up by? It's going up by 60 every time. 60, right? And it's doing that all the way down. What about the y's or t in this case, right? It's going up by 3 every time. This is that telltale sign that we've got a linear relation, right? If we graph this thing, this would be a straight line. All right. Determine whether each relation is linear. Explain why or why not. Okay, so the relationship between the cost to rent a dance hall and the number of people attending the dance. If the hall charges $200 plus $5 for each person who attends. All right. We did questions like this in Math 9. We could write this as y is equal to mx plus b. Okay, where we could have the cost. So instead of a y, I'm going to write c is equal to, and then in this case, the hall charge is $200 just flat, right? Like no matter what, I'm getting charged $200. That's like my b value, right? So no matter what, you could write it in here and be like, okay, that's plus 200, right? That's happening no matter what. And then the $5 for each person who attends. Well, I could call like the number of people who attend. I could call that maybe n instead of an x. Be the same thing though. And then it'd be $5 for every one of those, right? So $5 times the number of people who attend, and then plus my 200. So would this thing be a line or not? Yes. Yes, that's that y is equal to mx plus b. Yeah, so that's probably good enough. What about the relation described by this equation? X squared plus y squared is equal to 25.
No, because it's squared.
Yeah, and it's not going to be because of the squared, right? So I can see right away that would give me, well, actually that one ends up giving you a circle. If you do that one. Okay, what about this one? The relation described by the set of ordered pairs. So this time they didn't give us to us in a table, but remember the way this works, these are my x's, right? Every one of those are like my x's. So I'm really asking myself, are those going up or down by the same amount every time? So 10, 15, 20, so my x's are going up by 5 every time. What about my y's? So that's like y, y, y. So what are they doing? They're going down by 8 every time. So linear, non-linear? Linear. Yep. So that'd be a linear. Okay. So sorry, we just kind of talked about that one. I didn't actually write it down, but okay. Let's do. Let's do this one. Which of the following relations are linear? How do you know? First one's a little tricky, eh? Y is equal, or sorry, x is equal to -2. Yeah, do you remember we did this in Math 9 too, right? Do you remember when x was equal to a number, what that was? Was that a vertical line or a horizontal line? All right, how many people say horizontal? All right, how many people say vertical? All right, the verticals have it. Okay, so this is what's happening here. At -2, you'd have a straight line going through, right? What that's saying is x is -2 everywhere, right? So no matter what, x is -2. So, and this is a line, so yeah, this would still be linear. Okay, that's kind of a weird example, right? That one. The next one, y is equal to x plus 25. Yeah, that's that perfect y is equal to mx plus b situation, right? So in this case though, we'll go through graphing here in a bit. In this case, what is my m? 1. Yeah, there's still like a 1 sitting out front there. Yeah. What about c?
No, it's squared.
Yeah. So yeah, it won't be because of the squared, right? That'd be a parabola in the end. And then what about the 1 over x? No.
X can't be the number.
Yeah, x can't be in the denominator. Okay, good. All right, rate of change.
If x is a numerator,
Rate of change. All right, so this is where we're going to be figuring out how to graph these things and everything else. So rate of change is going to be the slope of our graph. And you guys in science, right, if you guys are doing physics, here, let's see, let's do a little quiz. If this was distance and this was time and I had a line going up like that, what does the slope of this graph represent?
Rise over run.
Yeah, and what does it represent though? Like what?
Distance over time. How far you make it over a certain amount of time.
So let's say we find the slope, so from there to there or something, right? The rise and the run. What number, and I find that to be a number, what did I find? I found the speed, right? That would be, so the slope of a distance time graph is the speed, right? Which is your rate of change, right? The speed is a rate of change. Speed is meters per second. It's saying how many meters are you changing every second, right? That's your rate of change. Does that kind of make sense? Yeah, okay, so when you guys are doing this in science, that's the same thing. We're just going to do other examples too. Maybe we'll have different rates of change other than just speed. Okay.
Oh yeah, I guess
so. So if we had, let's say, well, here, back up a little bit. Rate of change is the change in the independent or the dependent variable over the change in the independent variable. Okay, now that sounds a little confusing, but what that's saying is that the rate of change is really just how far you go up and down, which is your rise, right? That's your change in your dependent variable, right? Your change in your y, over your change in your x, over your change in your independent variable. Does that make sense? It's like, it really is just rise over run, is what we're saying there. So for example, say the cost of a car rental is $60, plus $20 for every 100 kilometers driven. The graph of this relation is shown to the right. The rate of change can be calculated. So in this case, right, you'd say the change in the cost. Okay, so the change in the cost, it's like every one of these blue arrows on this side. Can you guys see that it's going up by, well, 20, right? So in this case, it's going up by 20, right, in that one? So up by 20. And then your change in your distance, right, from this point to this point would be 100. So 20 over 100. And your units still could matter here too, right? Or they should matter. You've got $20 over 100 kilometers. So my answer should be in dollars. So that's 0.2 dollars per kilometer, right? Like your units will still work out. Yeah? Okay. Yeah, well, let's do some examples here. So yeah, so a popular event at, I'm not going to try to say that, is the fireworks display. Assume that the event organizers send up 20 fireworks shells each minute. Is the relationship between the total number of fireworks and the duration of the event linear or non-linear? Explain how you know. So what do you guys think? Okay, so in B, it says assign a variable to represent each quantity in the relation. Which variable is the dependent and independent? So really, let's make an equation. Let's do that first. We've kind of got that last, but I think it'll be better to do it first here. So in this case, let's say that the number of fireworks like in the air, or like that were actually fired off, let's call that F. Right, so here, we'll B down here. So we'll say F is equal to, F being the total number of fireworks that'll be fired off. Okay, now it says that organizers send up 20 fireworks shells each minute. Okay, so 20, and then maybe we'll call that, well, 20 fireworks shells every minute, right? So, I don't know, minute M? And that should be good, right? That should be like our y is equal to mx plus b, like y is equal to mx plus b. But what would my b be? Zero, right? We started at 0. It'd be different if there was already some in the air, or like we had already fired some off. That would be like where we started. But we didn't start off, so you could say that's plus 0. But there you go. That's our equation for that one, right? Okay. Now, let's create a table of values. So if we were creating a table of values for this one, so table of values. So here I'm going to C. And we'll call M on this side and F on this side. So M will be our independent variable and F will be our dependent variable. Okay, so if we're making a table of values, what numbers do I put in here? Yeah, 0 would be a good place to start from. Why don't they start from like -3 or something like that? You can't go back in time, right? So just make sure that it relates to the actual problem here. We'll start at time. We'll start at time equals 0. So 0, and then maybe 1, 2, 3. That's probably good enough. Okay, so at 0, how many have we fired off? 0. After 1 minute, how many have we fired off? 20, right? Because we just put a 1 in for M there, right? 20 times 1 would be 20. After 2 minutes, how many have we fired off? 40. After 3 minutes, 60. And there's that telltale sign. We're going up at the same amount every time. This is definitely a line. Yeah, that'd be a lot of fireworks, yeah. So there's our table, guys. Create a graph for this relation. So yeah, we could make a really nice graph, but let's just kind of make a sketch with what we got here. So the way this thing would look would be, okay, so we'd have a line like this. F is going to, or sorry, yeah, F will be on this side. This will be our dependent variable. And then M on the bottom. And then technically, we should be writing like, you know, that what we're measuring this in. So this would be like in minutes. And then F, you'd want to like describe it as like number of fireworks. Okay. Now, all right, so we kind of got a bit of an idea with our table here. We probably could just to graph this. It would go on forever, but if this is our time in minutes, right, on the bottom, then we could call this 0, right? And we want to go up till like 3 or 4. So just kind of make sure we can get there. So go like 1, 2, 3, 4. And then number of fireworks, what do I want to make sure I go up to? Yeah, so just make sure that we're going up by the right amount here. Let's go up by 20s. That'll be the easiest way to do it, right? So let's go up by like 20, 40, and then 60. Okay, so then after 1 minute, you're gonna have a dot right there. At 2 minutes, a dot at 40. And this should be lining up so it goes back to 0. And then 3 minutes, something like that, right? Okay. And then are the data discrete or continuous? Yeah, they are discrete, yeah. This one's a little bit funny though too, because technically there would be fireworks being fired in between. But there's only like a finite number that would be happening there, right? So yeah, it would be discrete data because you can't have half of a firework.
Well, I mean,
Yeah. So yeah, the data is going to be discrete. Now, what is the rate of change for this relation? So remember, rate of change is going to be like the slope of this graph, and it's going to be the difference in our independent variable, right? So if we like made like a, you know, rise over run situation here. All right, let's do a different color. So if we're not going to connect the dots, so it's not going to look like a normal line where we find the slope, but what would our like run be in this case? Like the difference? Yeah, it's going to be 1, right? 1 minute. And what would our rise be? 20 fireworks. Yeah, so 20. So our rate of change in this one would just be 20 or 20 over 1, and then that would be fireworks. Yeah, fireworks. Yeah, technically your units, right, would be like maybe F per second or per minute or something. Fireworks per minute. which would be like 20 over 1. That'd be the same thing too, right? Rise over run. Yeah. All right. All right, a hot tub contains 1,600 liters of water. Graph A represents the hot tub being filled at a constant rate. Graph B represents the hot tub being emptied at a constant rate. Identify the dependent and independent variables. So in this case, the hot tub being filled up, what would my independent variable be? Time or volume? Time, right? Time keeps ticking by no matter what, right? It's pretty independent of anything else. And then my dependent variable, the volume is going to depend on how much time goes by. So that's my dependent variable. Describe the domain and range. Okay, so domain and range on this one. Here, I'll do these beside these. So here, let's write down dependent, or sorry, independent. Dependent for volume. Okay, for B, describe the domain and range. So what would the domain of this guy be? So the domain, so D dot dot. Yeah, are we going to use X or are we going to use, what are we going to use here? Yeah, we'll use T. T is going to be greater than or equal to something? What's it going to be greater than or equal to? 0, right? It starts at time 0. And it's going to be less than or equal to 80. Right? That's when it's totally full. That's like our X value, like our Y value there. Like, that's as far over to the right as our X's get. Okay, range. Our range is going to be volume, so like V is greater than or equal to 0, right? It's empty. Or less than or equal to 1,600. All right, determine the rate of change. So the rate of change for this guy would be what? So here I'm going to pause for a second. Okay, so finding the rate of change on this guy, what we're going to do, we're going to make a triangle. Now I chose to make it there. I could have made this in multiple places, right? I'll show you in a second how it would be the same. But on this side, I've got, what's my run here? I've got 800, right, all the way from the bottom. And across the bottom, I've got 40. So this would be 800 liters over 40 minutes. So that would be 20 liters per minute. That's my rate of change, right? 20 liters every 1 minute. Right, is what's happening there? Yep. Okay. Now, I want you guys to see, though, this is what you guys were talking about before, is that this would be exactly the same if I chose to make my triangle, let's say, right here. Did anybody else make their triangle right there? It passes through that point nicely, right? Like, it doesn't show like a dot right there, but it does pass through nice right like that. So on this side now, we've got 400 over, and then this would be 20. 400 over 20 would also be 20 liters per minute. We could have also made the triangle all the way to the top, right? It could have been like from there to there. And then that would have been 1,600 over 80. 1,600 over 80 would again be 20, right? So the rate of change doesn't matter where we make that triangle, right? It's a ratio. That number always comes out the same no matter where you make the triangle. All right. Oh yeah, what's D say? Write an equation for each relation. All right. So write an equation for each relation. We're going to say D. So we'll say Y is equal to mx plus B is what we're after here. Or, you know, instead of Y's and X's, we should be saying volume and time. Okay, so this won't be so bad, guys. Volume is equal to, and our m value is our slope, right? That's been the slope like ever since grade 9. That is our rate of change, right? That's what we've been finding. So what am I going to put in for m? 20. So this is just 20 times t. And then the b value 0. It started at 0, right? So, yeah, good to go.
Wait, since it's 0, you just leave it.
Just leave it. We could write plus 0 if you like, but it doesn't do anything. All right, next one. So let's go. Okay, let's do the next one here. So, okay, describe the independent. It's going to be the same, right? For the last, so I'll start at B on the next one here. So for B, describe the domain and range. So the domain. So what are my x? So my x values, or my t values in this case, greater than or equal to 0 still, less than or equal to 40. Our range, our volume will be greater than or equal to 0 again, and less than or equal to 1600 again. C, so the rate of change now. So what would our rate of change be on this one? So let's do this again. So making a triangle again, I'm going to pick probably this one, a little bit smaller numbers. So now we've got 800 for our rise, and we've got 20 for our run. Okay, so 800 liters over 20 minutes. So what would that be? So 40 liters per minute. Right, so there's my slope. Now, the only thing to watch here, and you guys ran into this in your science unit too, right? Did anyone see what I probably did wrong here, or what I kind of missed? What's the difference between this graph and the other graph?
One's going down.
One's going down.
So it's be negative.
Negative, yeah. So technically this thing, when this went down here, I wrote 800, but this was really like negative 800. It's going like down 800. So my answer would be like negative 800. So then this would be like negative 40 liters per minute. It's like losing 40 liters every minute. Yeah, if it goes down, it's a negative. And that'll be for math and science. That's the rule. Okay. Okay, and then write the equation. So in this case now, so we're going to say, so D, we'll say volume is equal to, okay, what's our slope? Negative 40. And then times T. And then what's our, nice, yeah, we started at 1600, right? So it's going to be plus 1600. That's our B value. Do you guys see that our B value, that'll always be the case? It's where it crosses the y axis. It's like where you start from. It'll always be the y-intercept. Okay?